I think I'm gonna get started. Hello everyone, welcome to the CCAT Research Review. My name is Henry Liu. I am the director of CCAT at the University of Michigan. We are the USDOT's Region 5 University Transportation Center with consortium members including University of Akron, Central State University, the University of Illinois Urbana-Champaign, Purdue University, and the Washtenaw Community College. We do have a few upcoming events we want to bring to your attention. First is our distinguished lecture series with Professor Azim Askandaran of Virginia Tech. Is scheduled for March 24th at 2 p.m. And this one will be hosted at University of Michigan's Transportation Research Institute. The registration to the Distinguished Lecture Series is free and can be found on the CCAT website. Second, April 14th and 15th, we will be hosting our annual Global Symposium on Connected Automated Vehicle and Infrastructure at Washtenaw Community College in Ann Arbor. Keynote speakers for the symposium include Diana Fitchgott-Roth, the Deputy Assistant Secretary for Research and Technology at the USDOT, and Professor Hui Peng, Director of MCity. You can register the symposium at ccat.eventbrite.com, and early bird pricing is in effect through March 10th. On a bi-monthly basis, we host this free webinar series as a way to highlight the cutting-edge research being led by our consortium members. At CCAT, we conduct research with the end goal of technology transfer, moving ideas to real-world practice. Today's research review is presented by Dr. Sikai Chen and Sam Labi from Purdue University. Dr. Chen is a postdoc researcher at CCAT and the Next Generation Transportation System Center, also known as NEXTRANS. And he's also a visiting research fellow at Robotics Institute at Carnegie Mellon University. His current research focuses on deep learning, intelligent transportation systems, vehicle automation, and simulation and control. Dr. Sam Labi is a professor at Purdue University School of Civil Engineering. He's also the director of NEXTRANS and associate director for CCAT. Research includes data analytics for smart monitoring and maintenance of infrastructure, as well as automation and connectedness of infrastructure system component and functions. Please go to menti.com, MENTI.com, and enter the code 65, 57, and 49. This is also on the slides showing to you on the screen right now to ask questions. Before we start, please be sure to mute your microphone for the duration of the presentation. Without any further ado, let's begin.
Okay, thank you, Henry. And welcome everybody to this first edition of the CCAT Research Review Series. We at the Purdue CCAT Research Team are very honored to have the opportunity to be speaking with you this afternoon. Before we start, I'd like to acknowledge the tireless efforts of UMichigan's CCAT team, including Professor Liu and Debbie, Bezina, and Calvin, and Francine. So thank you very much for making things very smooth for us. The title of our presentation today is Crash Avoidance Framework for Autonomous Vehicles Under Crash Imminent Situations. And this presentation is being given by myself and Dr. Chen. And we have been introduced already by Henry. So I would like to also mention the names of the other research team members who are here with us. They're seated here. So Ms. Rain Dew, Ms. Yujie Lee, Mr. Paul Ha, Mr. Frank Dong, and Mr. Trevor Moore is not here yet. You may kindly wait. You may kindly follow the instructions that Professor Liu has given for asking questions. Next one. This slide. Okay. So then I'll give you a brief background of what we're gonna talk about. We're gonna start with a CCAT research overview, then a background of or motivation of what we're going to discuss. This will be followed by the methodology that we are using, and a small demonstration. And I must add that this is a work in progress. We began in January, so we don't have everything to show right now, but we wanted to at least to share what we have so far with you all to get your ideas, get your input, and have a good discussion. So the next slide, slide 2, shows the CCAT research activities, or some will call it the themes of the CCAT research: policy and planning, human factors, infrastructure preparedness, operations and controls, modeling and implementation, and enabling technologies. Now you see that 3 of those 6 themes have been highlighted in black. That simply says that this current presentation we are giving is very strongly related to those 3 themes or research activities that we have highlighted. Now, we all know that safety is a big issue, and I'm going to discuss safety because that is the primary motivation for our research, for this research. And this motivation arises from 2 realizations. The first is that when accidents happen, mostly is due to human mistakes, the mistakes of the human driver. And secondly, the realization that if AV controllers can be designed very well, then they can help reduce the number of crashes. When we heard about the AVs initially about 10 years ago, we all heralded the advent of this new technology, saying that at last we have a permanent solution to crashes. But it's a double-edged sword, because whereas the AVs will eliminate the errors due to humans, it could also lead to some crashes, at least in the short term or in the transition period. So this research is primarily geared to address the mixed traffic stream that we shall be having in the transition period. All right, so traveler safety is a big concern, huge concern, and a lot of people still die on our roads. In the US alone, 40,000 people die every year, and about 10 times that number are injured, and many more accidents occur in property damage. Worldwide, the number is about 2 million, 1.2 million fatalities per year, and it causes a lot of pain and suffering, besides just the loss of human life, which is not just, by the way, but it causes pain and suffering. In some cases, the primary income earner loses life, and the family is left destitute. So traffic accidents are not only medical, but also a social problem that has to be addressed. Now, the NTHSE has estimated that 95% of all crashes are directly or indirectly related to the human mistakes, the mistakes that the human make. And this is a statistic that we have seen over the years consistently. Over the past 4 decades, different research have come up with different numbers, all ranging from 90% to around 98%. So there's no question that the mistakes that we human drivers make are mostly responsible for crashes. So this serves as a primary motivation for the research, for this research. Now, the question is, how do we reduce the number of crashes? Or at least reduce their intensity? Well, just like I said, we can eliminate or reduce the errors that the human beings make. That's one way. And if you're able to do this, then we are gearing towards something we call Vision Zero. Vision Zero. Vision Zero is an international initiative that is geared towards elimination of crashes. Some see it as a utopian goal, but at least it's a goal, and we can all work towards that. And automation offers probably the most promising solution, or the most promising path towards Vision Zero. Now, if I may expand a little bit on the mistakes that humans make, the causes of these mistakes are overconfidence. Many of us feel that we are good drivers, whereas we are not often, not as good as we think. We also have problems of distractions, especially among the youth. Texting, music, and all that. Fatigue. Sometimes we're just tired and we lose concentration. In some cases, it's driving under the influence of some substance or medication, and sometimes it's just slow reaction times, which again, it's maybe due to some human feelings or tiredness or some other reason. All right, so these are things that is difficult to avoid or reduce, but ultimately they translate into crashes. So therein comes in the promise of automation. If through automation we can let the vehicle be controlled by something other than human being, then no matter how tired the human being is, or how inebriated he or she is, and how distracted, well, there's some guarantee that the traveler will get to his or her destination in one piece. So that's the promise of automation. Now the next slide, the slide that we are showing on slide number 5. Here, I'm going to show you a couple of short videos actually, and this involves driving simulation and macro simulation along a corridor. Later on, I'll return to these videos, or we shall return to these videos to reinforce our crash avoidance methodology. But in the first video that you see here, our teammate Trevor deliberately drives in a very erratic manner on a simulated roadway environment. And if I may click, yes, okay. And you will see him weaving in and out dangerously. And in doing so, he poses a safety hazard, not only to himself, but to other vehicles in the vicinity. Clearly, any autonomous vehicle in the vicinity will need to take evasive maneuvers in order to avoid trouble. And as a side note, I can assure you that this is not the way he drives in real life. Otherwise, we will not be finding him. Okay, all right, so go to the next slide. So the next slide shows a little bit of micro simulation there. We see a side swipe or side impact accident. Then you can see that, I think I can click, right? Or is the next video? Okay, no, don't click here. Let's go back. Okay, sorry. So in the second video, on this slide number 6, and the video is on the slide number 7. So if you can just hang on. But what you will see in the video, you will see an autonomous vehicle, a red car, that shares the traffic space with other vehicles. You will notice that the human-driven vehicle, the yellow car, suddenly enters the lane in front of the AV. It cuts in, and the AV decelerates in order to avoid rear-ending the HDV. But in doing so, the AV itself, the autonomous vehicle itself, is rear-ended by the immediate following vehicle behind it. So this short video exemplifies a potential situation where two crash patterns could be experienced: side impact or side swipe and the rear end. So let's play the video. It's a very short clip, just a few seconds. So just play it and let's see. Yes, right there. So we are just playing it over and over again, so you can register the point. Okay, I think that's enough. Okay, so next slide. Okay, so next, yes. So this is the second video, right? Okay, so I think the point is made. Okay, so these short videos remind us of the potential traffic safety hazard, the risks that await us in the transition period, in the transition phase of AVs, where both the AVs and the HDVs, HDV means human-driven vehicle, where they both share the traffic space, until a time when we have 100% market penetration. Well, it is not certain when we shall achieve that 100% market penetration. It's not even certain when we shall even start the AVs. The AV sunrise, yes. Of course, we have AVs right now on test tracks and restricted environments and all that, but we're not really sure when it's going to be open for public use. It's possible that the start year may be different for different corridors or road classes. That's possible, not the entire network at a time. So that's a possibility. But whatever the case, where we have a mixed traffic, we'll have to contend with that heterogeneity of AVs and HDVs and their sibling rivalries and interactions. That's something that we have to contend with. So this will mean that the algorithms in the AV controller will need to be designed to make the AV proactive, very proactive, to mitigate the mistakes that the HDV drivers make and the bad habits of the surrounding HDVs in the vicinity. So this is a primary motivation of our research. And the next few slides, I'll give over to Dr. Sikai Chen, to come and give some two perspectives regarding the crashes that will involve autonomous vehicles. So Sikai, over to you.
Okay, thank you, Dr. Labi, for introducing our project background. As Dr. Labi mentioned, in the first few decades of autonomous vehicle deployment, there will be a mixed traffic of autonomous vehicle and human-driven vehicles on the street at the same time. So this means that human error will still exist in the traffic stream, while autonomous vehicles are indeed expected to reduce the number of crashes. There will still unfortunately be crashes there. So in the mixed traffic, we believe that there will be two main perspectives of crashes that involve autonomous vehicles. The first one is when the autonomous vehicle is at fault. It's self-explanatory. Reasons like algorithm failure or mechanical issues can cause an autonomous vehicle to perform dangerously, and that may result in a crash. This is also a huge concern for autonomous vehicle developers and manufacturers. So naturally, it receives a lot of attention. What we want to bring into discussion in this project is perspective 2, where the surrounding human-driven vehicles or the HDVs are at fault, but the AVs were unable to avoid the crash. These situations will exist when autonomous vehicle cannot figure out a way to avoid crash induced by human drivers. In the remainder of this presentation, we will mainly focus on the perspective 2 collision and provide some thought on how we are going to address them. We mentioned previously that the emerging technology will expect to improve safety. One such technology is through the connectivity. To give a very broad definition of that, it is the ability for vehicles to share and receive information from other vehicles and infrastructures. To human driver sitting in the connected vehicles, connectivity will allow them to receive information regarding unsafe circumstances in advance, even without a clear line of sight. As you can see in this figure, we have two connected vehicles indicated by the blue color. When the blue vehicle on the right suddenly stops, the vehicle on the left will receive the sudden stop information in a very short amount of time through the connectivity. This will provide the driver with more time to react. And this is just one example about how the connectivity can provide safety benefits to human drivers. However, the connectivity with human drivers has some limitations. The most important limitation is that it really depends on the driver's compliance. The driver can choose not to do anything with the information, or maybe the driver simply cannot react to the information fast enough. Both of these may lead to a crash. And similarly, there could also be limitations regarding information delivery modality. Time-sensitive information, such as the information directly related to a potential crash, should be delivered efficiently. Since a driver may also respond to various forms of information modalities in different ways, this the difference could also cause some problems. For example, the slow reactions. Another emerging technology is that that can improve safety is vehicle automation. The effect of automation is quite straightforward. It directly removes the human inputs and the associated human errors from the vehicle. Engineers and scientists have been developing and enhancing technologies that could outperform human drivers in terms of accuracy, reliability, reaction speed, and so on. This includes the advancement in sensors technologies such as LiDAR, radar, camera, and the algorithm side, we have the computer vision, objective recognition, 3D reconstruction, motion planning, and so on in real time. With these technologies, vehicles, in terms of its own driving, will not be subjected to human errors. But the limitation here is that this only eliminates human error from within the vehicle, as we discussed as the perspective one, where the autonomous vehicle is at fault. However, if there is someone who wants to hit you, and as what we saw in one of the previous videos, where the driver made a sharp lane changing without seeing you in his blind spot, there will still be a crash. In addition, if we only use the sensors, there will always be data limitations. Well, connectivity alone and automation alone has these limitations. We believe a system of CVs and connected human-driven vehicles can address their limitations. This combination of both connectivity and automation will enable cooperative control between connected vehicles. This means that they will share information among each other and make well-informed cooperative decisions for their benefit as a whole system. Specifically for the roadway safety, since connected human-driven vehicle will be cooperative, CV will then have more room to make a safe maneuver. And if this maneuver is able to help to avoid a crash, then everybody in this area will get benefit. In order to realize this cooperative control, we will temporarily override the speed control of the surrounding connected and human-driven vehicles in the crash imminent situations. This can be considered as an extension of some of the existing concepts, such as cooperative adaptive cruise control, where the drivers do not really need to control their speed. By doing this, we will be able to avoid some crashes that human drivers are unable to avoid right now. So this will help to contribute to the goal of Vision Zero, of zero fatalities. Given the system of control, the purpose of this research project is to design and test for CEVs to avoid crash imminent situations through the use of both connectivity and automation. Our first method that we will present here is a control-based approach. In general, control systems deal with behavior of dynamical systems. The dynamics of the system serve as inputs of the controller, and the object for the system is to perform your desired action. Here we can see in the figure a simple feedback system where the controller accounts for the desired output and the measured error to eventually stabilize the desired system's output. With this in mind, we can now discuss the concept, the context of our system and the desired output of the system. Our scenario is that there will be an aggressive driver who suddenly changed the lane into an autonomous vehicle's trajectory due to an driving error. In the following slides, the red vehicle will be connected and autonomous. The yellow vehicles are the aggressive lane-changing vehicles. The blue vehicles will represent the cooperative connected and human-driven vehicles that will help to avoid the crash. And the white vehicle will be a non-connected vehicle, where in the literature, people also call them isolated HDVs. For the control-based methodology, we will explore two maneuvers for the CV to avoid a collision. The first one is that the CV will decelerate to allow the lane-changing vehicle to enter its lane. In this case, the connected vehicle driving behind the CV will decelerate in cooperation with the CV. The second maneuver is a bit more complicated compared to the first one. As you can see from this figure, when the vehicle behind the CV is a non-connected human-driven vehicle that follows pretty closely, if the CV now take a hard brake to avoid the hit from the yellow vehicle, then there's a high chance that the white vehicle will run into the CV and there will be a rear-end collision. So in this case, our CV will try to perform a lane-changing maneuver to avoid the yellow vehicle from its hitting. And the blue connected vehicles in the target lane will try to create an opening for the CV to enter. The information that a CV will have access to is the following. So first, we will have the vehicle speed and position data in real time. For the connected vehicle, this information can be shared through connectivity, while for the aggressive human-driven vehicle that's changing his lane, we will need to rely on the sensor on board of the CV. Secondly, the CV need to know the distribution of the existence of the surrounding connected vehicle in its area. So the CV can know in which direction there will be other vehicles that are able to help to create more room for its safe maneuver. In addition, we will also need to have the real-time predicted trajectory for the aggressive lane-changing vehicle, so we can compute the potential collision point in real time and do the path planning to avoid it. Given this information, the CV must determine the crash avoidance maneuver and calculate the input parameters to perform the maneuver. One thing to emphasize here is that the whole process from determining the avoidance maneuver to the execution of the maneuver must be done quickly enough to actually avoid the crash, as there will be no benefit to figure out how to dodge an incoming vehicle after the crash. This slide shows the general flow of our control framework. First, we will have a motion prediction component that predicts the trajectory and speed profile of the aggressive lane-changing vehicle. With this information, describing the lane-changing vehicle's behavior, the framework will choose the appropriate maneuver to avoid the crash. After the crash avoidance maneuver is decided, we need to make sure that in the surrounding area, the CVs and CHGVs will act cooperatively to dodge the hit. There are some challenges that we need to pay attention to for the control framework. The first is that the robustness. Since we are talking about an aggressive driver whose behavior could be highly unpredictable, so it can be expected that for the motion prediction part, there will be some error introduced. And we need to make sure that our framework is robust enough to deal with that. The second thing is we need to pay attention to its stability. As crashes typically happen within seconds, we need to make sure that the control can be stabilized in that short amount of time. The second approach that we are considering in this study is learning-based approach. In this project, we will explore reinforcement learning algorithms, which let the agents to interact with an environment. And there will be a feedback loop of the learning between the agent and the environment. Our agents here are the connected and autonomous vehicle and the connected and human-driven vehicles. They will take a series of actions to explore the environment. And each time when they take an action, they will be evaluated by a reward function telling them how well they are doing right now in terms of their safety performance. and also what the state they will move into, so they can take actions in the next steps. By doing this, we are trying to let the AI to learn an optimal crash avoidance policy defined by the argmax function shown here, where we want to maximize the total accumulated reward for the CV and CHDVs to see what they will get in this learning environment. The reason that we want to explore the reinforcement learning is that it does not require an explicit definition of the crash patterns. And we also do not need to define the specific actions that the agents need to perform. This will allow to account for the collision situations that are not predefined. As you can see in the last video, the red CEV will try to decelerate in different ways to avoid the hit. When it's not successful, the cumulative reward for this series of actions that it took will be generally low. As a comparison in the right video, the CV and the CHDVs are able to act cooperatively and dodge the hit by doing deceleration. In that case, it will generally yield a high cumulative reward. These slides summarize two types of the learning-based cooperative control. The first one is a centralized learning. In this case, there will be a single intelligent controller making decisions for both CV and CHDVs. The advantage is that the cooperation is implicit, meaning that there will be a single reward function to evaluate and the performance of the agents. When convergence occurs, this type of design is expected to yield a superior learning outcome. And also, the controller design is relatively less complex compared to the second type, which is decentralized learning. The main difference here is that we will have a separate intelligent controller to make decisions for each agent. The advantage of decentralized framework is that it is relatively easy to scale up and have a higher chance to converge in large scale. In addition, the agent's network is also more robust because if one of the agents has some issues, the other agents will still try to perform well since they are controlled separately. With the control-based and reinforcement learning-based method, we can move on to the deployment for validation and operation. We classify 4 phases of deployment of our design framework. The phase 1 is done on simulators in the simulated environment at Purdue. We have a driving simulator which can also work with commercialized software for the traffic simulation. We can deploy our system into this simulated environment to assess their performance. And we can also recruit human subjects to evaluate if there are any major flaws with respect to our the human-machine interactions. Phase 2 is done in a controlled and small-scaled environment in the real world. We have the access to scaled vehicles such as the Amazon Web Service debriser that can readily accept our developed control system. Phase 3 is done in controlled real-world environments such as the M City in Michigan, the NTU self-driving bus route, and so on. And lastly, for the phase 4 deployment, they will be done in urban streets and highways. It is our goal to deploy our systems according to these 4 phases. This is an example showing the phase 1 deployment in the simulated environment. We see our colleague Trevor again driving the yellow vehicle using the scanner simulator that we have at the Purdue CCAT Center. He's still taxiing and driving and changing his lane aggressively. And our framework will try to predict his lane changing trajectory and make cooperative decisions for the CV and CHDVs in the surrounding area to dodge the heat. Here is a phase 2 deployment in a controlled small-scale environment. It's actually the hallway near our office at the Purdue CCAT Center, where the Amazon Web Service deep racer vehicles are used to demonstrate the deceleration and the lane changing maneuver to dodge the potential heat. For now, we only have 2 deep racer vehicles shown in this video. We plan to increase the number of them to simulate more complicated real-world scenarios. In this presentation, we started with the background introduction with emphasis on the roadway safety. We discussed the mixed traffic flow in the transition period, where the autonomous vehicle and human-driven vehicles are both on the street. And we talk about the 2 perspectives regarding the crashes that involve autonomous vehicles. Then we talk about the concept of cooperative control for crash avoidance and introduce the control-based and learning-based crash avoidance frameworks. This project is in alignment with the US DOT's focus on the CV technology deployment, for which we introduced the 4 phases of the deployment. I would like to take this opportunity to thank our sponsors and friends who always provide support to our research and share their valuable insights and to advise us. Here we have the US DOT and the Discovery Park and the School of Civil Engineering at Purdue University and all the CCAT consortium members. Thank you very much for all your support. In addition, I also want to thank my amazing team at Purdue CCAT, our center director, Dr. Samuel Labi, and our amazing CV and enabling technology group. We have many talented and hardworking students here. It's my privilege to have the chance of working with them. We have Mr. Pao Ha, Mr. Ji Xiandong, and Mrs. Renjia Du, Yu Jie Li, and Mr. Trevor Moore.
Great.
Yeah, thank you very much for attention. Any questions and comments are much appreciated.
We have one question that asks, have you given thought to how the connected HDV driver would feel about the sudden rapid deceleration that might be required to accommodate changing lanes?
I'm sorry, I think
Can you repeat?
Yes, could you please repeat the question? I think I missed part of it.
So the question asks, have you given thought how the connected HDV driver would feel about the sudden rapid deceleration that might be required to accommodate the dodging AV changing lanes?
Yes, so when we evaluate our framework, we can also consider like the comfortness. So we can put that into our control framework. But for now, since this crash like typically happened within seconds, so our priority is still to try to dodge the crash. But later on, when we, like for instance, when we do the learning-based framework, we can try to take off the driver's comfortness.
Comfort.
Yeah.
Okay.
Yeah, driver's comfort.
Oh, okay. Into the reward function.
Yes. Yes. Yeah. So we will be able to change our reward function to maybe, so for instance, put like jerk into consideration. So we hope there will not be like the sharp deceleration.
Like the number of jerks and the intensity of the jerk.
Yes.
Okay. We have another question. Because all vehicles are cooperating, it appears the aggressive driver is being rewarded, as there will be no near misses. How do we deal with the issue of rewarding aggressive drivers?
Yes, I think this is a very valid concern. For now, for the focus of this study, we didn't take off that, but I think later on we have to think about that. Since I think you are perfectly correct. Since human drivers are pretty smart, so maybe later on when they see there's an autonomous vehicle and who can dodge the crash, they just run into them and just take the lane they want. I think there might be a problem.
Yes. Yes. So this is some Labi. So that is right. And as with all human beings, once we tend to see a safe environment or a perceived safe environment, we tend to behave in ways that are risky. This is called risk compensation, in driving. And we haven't yet considered that in our methodology, but ultimately we have to consider that, and that's a good question.
Yeah.
Okay. Have you considered real fatality/crash statistics in choosing the scenario for your analysis?
Yes, correct. I think that is a very good question. So actually, if I can go back to our control framework in a few slides here. So here, when for our control-based methodology, when we need to decide which maneuver we need to take, as you can see here, we will, if the deceleration strategy is feasible, we will choose it over the lane changing maneuver. The reason we did this is because in the past study, there were research found that the vehicle's crash, the vehicle speed at crash is highly correlated with crash severity level. So meaning that when the vehicle is crashed at a pretty low speed, there's pretty low chance for a fatality compared to when the vehicle is crashing at a high speed. So that's why we have this general logic. If something is still going wrong, since as we mentioned, there will be the prediction error introduced by the aggressive lane changing driver. So maybe when the error is introduced, there will still be a crash, but we tend to let it to crash at a low speed.
And to add to that, this is some Labi here. To add to that, on the typical 3-lane freeway, the statistics show rear ending due to speed, the decelerations upstream, and also side swipes tend to be very frequent compared to the other types of crashes. So our initial scenarios that involve this type of crashes, yes, they were based on on the statistics of what kinds of crashes occur out there on a typical 3-lane freeway. So our scenarios that you see here are for 3-lane freeways. You see those 3 lanes, but this is just the beginning. There are other scenarios that we will consider, not just freeways, but also urban roads and other kinds of roads. And when we get to those kinds of roads, we shall look at the statistics and see what are the predominant type of crashes that occur on those kinds of roads and use them to develop our scenarios.
Okay, we have another question that asks if you have compared the two methods.
For now, we haven't reached to that point, since for the reimbursement learning-based approach, it's just the beginning. So here we are trying to show some intermediate result of the training, but we still are not very satisfied with our result. Since the project just started in January, so we haven't finished everything. Yeah, and the cases here are also pretty simple. In this case, for now, we only have 2 lanes, and we only try to test how the vehicle should decelerate. Yeah, but we are gonna definitely gonna compare them in the future. Yeah, thank you for pointing that out.
Yes, and actually, this is some Labi here, and actually that's one of the motivations for our deployment. Because it's only through deployment that we can tell whether which one works better. So so that's a motivation, and that's one of our goals of our research as well in our research statement. So something that we shall definitely be doing, definitely.
Okay, the next question, will the solution require cloud connectivity, or can the necessary processing be accomplished on board the vehicle via edge computing?
I think that is like a future goal. So for now, we're only doing this in the simulation environment. But I guess in the future we will like go into that area.
You want to see something?
Yeah.
All right. Okay. So Frank is here to, one of the team members is to give us, to share, come around, to share his, you have to come around. The mic, right? Yeah.
Yeah, it shouldn't be much.
Okay. All right. Okay. So Frank, go ahead, please.
So currently we consider the reinforcement learning using the very simple neural networks, not very deep. And our ultimate goal is to use such like the tiny neural networks that can be embedded into the edge devices and embedded into the vehicle itself, which doesn't need a high kind of computational power. So this is our future goal, but in the initial stage, we consider this problem and we want to address it from the beginning. So we choose to use some simple kind of neural networks instead of the very deep ones. Yeah, and with the connectivity, the devices, we can get more accurate information without any kind of deep pre-processing. So this is also a contribution to the simple neural network. Yeah.
Okay. So the next question, how can the RL approach adapt to slightly different scenarios than the ones trained for? And how many scenarios was it trained on?
So for now, so as we mentioned, for now we only created like pretty simple scenarios now. But like moving in the next few months, we are gonna try to maybe so eventually we want to be like in the simulation, we have the random initialization for all the scenarios. So the learning could be more robust.
Okay, I don't think we have any more questions, so I think we'll wrap things up here.
Okay.
So thank you for everyone for attending, and please be sure to register for the CCAT Global Symposium and the Distinguished Lecture Series with Professor Azim Eskandarian from Virginia Tech. You can register for both of those things at the CCAT website, which is ccat.umtree.umich.edu. Thank you, everyone.